Okay, I think I can probably get us started now. All right, so welcome to day 2. Yesterday we went over basic data structures as well as how to deal with object-oriented programming in Python, how to access objects, how to work with them, how to make them. Today I'm going to go a little bit into computer science and understanding how things are stored in memory and why certain Python packages exist for what seems to be the purpose of trading off flexibility for performance. So in a computer language like C++, those languages have real arrays. So a true array is where you have a bunch of homogeneous data structures, such as integers or strings or whatever else, but they're stored in memory and they're all stored in a row. So for example, a 10 integer array in C or C++ would be stored as just some other stuff, and then 10 blocks for integers, and then who knows what else. This actually leads to some security issues. So if anybody remembers a Heartbleed bug from a couple of years ago where everybody was afraid their passwords got leaked, essentially this is what happened was people were talking to servers and telling servers to basically respond to them with a message. So they'd say, server, say potato back to me. And this is how, when you have a secure internet session going, the server and your computer kind of know that they're talking to each other. So in this case, the person would say, say potato, it's 6 letters, and they would say potato. Say bird, it's 4 letters, server says bird. And then they would ask for something like hat, but they would say it's much longer. And that would cause the computer to read past the end of the, in this case, the string, which again is just an array of characters. So since it's reading beyond the end, it's going to just keep reading, and it's going to potentially read out random stuff from memory. And when it's reading out random stuff from memory, it's going to give people, who knows what, but potentially stuff you don't want them to. So Python uses something called pointers for flexibility. So Python isn't storing a list, for example, the list of 10 integers in an array. It's actually just storing them in random places in memory, along with links to them. So in Python, a 10 integer list actually goes 0, and then you have a pointer here telling you 1 is over here, telling you 2 is over here, 3 is over here, 4 is over here, 5 is over here, 6 over here, 7 over here, 8 over here, 9 over here. This is a little bit less efficient for a reason I'll get into in a moment, but it's a lot more flexible. So as an example, let's say I want to delete a number from this 10 integer list. So I just deleted a number. And all I have to do to deal with that is just adjust the pointers so that 1 now points to 3. If I want to add back 2, then I just store 2 somewhere in memory. And I now have 1 pointing back to 2 and 2 pointing ahead to 3. So a lot more flexibility. If I want to replace a number with a 10 in a 10 integer list with a string, so I actually want to get rid of a number and just replace it with some characters, that's easy enough to do. I store that in memory somewhere. And instead of pointing to 2, these now point to the string. And then I get rid of 2. So what Numpy does in Python, it gives you access to true arrays and true matrices. And by true arrays and matrices, I mean those data structures where everything is stored in a row in memory. So you lose flexibility. You can't arbitrarily add or remove stuff to a Numpy array, and you can't have heterogeneous data sets. It has to be all one homogeneous type. There's also a certain amount of overhead that comes from converting data from Python native structures to Numpy data structures. So the question comes up, why on earth would we want to do this? And it turns out that if you take a true array from C++ or one of those similar languages, stuff on a computer board doesn't happen instantly. It happens fast, but not completely instantly. So your CPU has to request values from memory. So if your CPU requests the first value from this array, the memory is going to return that value and send it off to the CPU. There's something called prefetching though. And what prefetching does is if your computer is accessing a chunk of memory, but it's accessing it either in order in the forward direction or in order in the reverse direction, prefetching will start sending data to your CPU before your CPU even asks for it. So you can kind of imagine that instead of the CPU asking for 0, having to make the request, having to wait for the request to be responded to, and then processing 0 and then making the request for 1, well, your computer's doing whatever it's doing with 0, the memory fetcher is already returning it the next value it needs. So it's basically like hooking it up to a big fire hose of data to process as quickly as possible. And that's essentially what prefetching does, and that's why these arrays are an improvement. So we're going to sort of prove this to ourselves, and there's actually another advantage to doing this as well. There's a lot of functionality that computers can do by doing mathematical operations on binary numbers, and there's certain calculations that are optimized for binary. So for example, there's something called the fast Fourier transformation, which Fourier transformations take a while, but fast Fourier takes a lot of time off of that. And fast Fourier is optimized for a system that counts in binary. So let's kind of prove this to ourselves and learn a few useful functions. And I believe the program we are going to use is called dot product test. Or I'm sorry, it's called Numpy speed comparison. So everybody get ready to work with Numpy speed comparison. And I'll just explain quickly what we're doing. So we're going to import Numpy. Obviously, we need to import Numpy to have Numpy's functionality. We're going to import random to have random number generation. We're also going to import datetime. And datetime is just going to let us calculate time something takes. We're setting a length here of 100, and that's just how long our arrays are, or our matrices are. So we're going to build up a couple of matrices. So in this case, we have our first matrix for Python functionality, and that's just doing a Gaussian distribution between 0 and 1 times length. So it's basically going to just generate 100 random numbers between 0 and 1. The second matrix is doing literally the same thing. We're also going to do the same thing in NumPy using NumPy's native random number generator, which by default goes to a Gaussian distribution between 0 and 1. So functionally, these are the same. They're just creating slightly different data structures. And we set our iterations to 100,000. So whatever we do, we're going to do 100,000 times. I have a couple of functions down here. So I have the manual dot product, and that's going to be using the Python native, the sort of some native Python code for doing dot product calculation. There's going to be the NumPy dot product, and then we have functions that will run both. So there's run manual and run NumPy. And here's what we're actually timing. We're going to run manual. So this is going to be the Python native. And we're going to run the first Python matrix, the second Python matrix, and we're going to run it for 100,000 iterations like we set. And it'll tell us how long it took to run it. We're then going to run the NumPy version. So we're going to use the NumPy matrices, but we're going to use the NumPy matrices using the Python native functionality. And then finally, we're going to run the NumPy functionality using the NumPy matrices. Again, we're doing all these 100,000 times so that we can actually build up a good separation in times. So go ahead and run that. I'll give everybody a minute or two, and then we'll pick it up again. And feel free to play around with the lengths and iterations just to see how it performs at different with different operations. But you'll see that pretty much at any setting, it's going to be faster to do it using all NumPy native. And of course, if you have any questions or if you find anything interesting, feel free to chime in chat, and I'll keep an eye on that for you. All right, quick show of hands, who's gotten this to run and who's gotten to mess around with it a little bit? All right, looks like a lot of people got to run this already. All right, so what you probably saw is using the Python native data structures and using the Python native methods. We can do this dot product 100,000 times in a little over half a second, which is pretty impressive already. If we do NumPy method using the or NumPy arrays using the Python native method, so using just pure Python, it takes about 3.5 seconds. So that actually slowed it down a lot. And the reason why is that it has to convert the NumPy arrays back to Python native structures. So 100,000 times, it's basically converting the same data to the same format. Using NumPy and NumPy's dot product generator, we actually cut the time from 0.65 seconds down to 0.5 seconds. So that's a fairly impressive improvement there. That's like a 13-fold improvement about. And again, this is the advantage of using the arrays that are sort of optimally stored in memory, and the methods that are optimized for doing binary arithmetic. All right, so in NumPy we did our dot product example, and now we're going to do a little bit of extension of our samline object from yesterday. So in order to do this, I have to teach a little bit about quality scores, and this will also help you understand how and why some data are encoded. So people who are either taking my morning class on sequencing or who deal with sequencing have probably seen quality strings before. So quality strings are attempting to describe the sequencer's confidence in each base call. And the way they're encoded is they're encoded using ASCII. So anybody out there know what ASCII is and why it exists? Feel free to chime in on the chat. All right, I got one answer saying characters, I think. I have somebody saying shapes on old websites. I don't think I met you, but you are awesome. And ASCII art is totally a thing. All right, so anybody know sort of the main reason, anybody out there know the reason why ASCII really exists? All right, ASCII stands for, I think, American Standard Computer Information Interchange, or something like that. Computers can't really deal with letters. Computers can't deal with words. Computers can't even really count beyond 1. But the nice thing about that is we can just make them count to 1 a bunch of times, and they eventually start forming bigger numbers. But computers can really only deal with numbers. So the way you get a computer to deal with letters is you start assigning each letter a numerical code. Now the world would be really difficult if Apple decided that they had some table of how they're going to translate letters to numbers, and Microsoft had some table of how they translate letters to numbers, and Linux had their own standard for that. And even worse, every few years, maybe they change. So there's got to be a better way, and it turns out there is. And ASCII somewhat even predates computers. So ASCII actually goes back to the days of teletypes, where I would type on my typewriter here, and it would actually print out in some other location, or maybe in several other locations. But the teletypes as well had kind of their standard for which number encodes to which character. And it just turns out that computers basically said, okay, we're just going to adopt this. So ASCII provides pretty much a universal table of converting letters to numbers. And if anybody's seen the movie The Martian, you saw him using this when he had to communicate with NASA, and he could only send them a few numbers instead of being able to access the alphabet. Or I should say, they could only send him some numbers instead of being able to access the entire alphabet. So we have a table for converting characters to numbers. And it turns out this table starts, obviously, so the first ASCII character is numbered 0, and that's just a null. But really, you want to start your ASCII characters for quality score encoding at 33, because everything prior to 33 is called a non-printing character. So it's going to be something like a tab, or a carriage return, or a line feed, or some printer control command. Because it turns out that there's a lot of non-printing characters early on in ASCII. So exclamation is the first character that actually prints on the screen. So the initial quality score encoding idea was we'll start at 33. Another group got the idea, hey, let's make our own quality score encoding scheme, because why not? So they started theirs at 64, which is the @ symbol. And what this resulted in is the original Sanger quality score encoding scheme started at what's called base 33, so it starts with the exclamation point. Alexa and some of the earlier Illumina setups started at base 64, so they started with the @ symbol being equivalent to 0. And then Illumina said, you know what, actually Sanger was probably a more popular scheme, so let's actually just roll back to Sanger. So came up with 2 standards. Now there's only really one that's in use, which is Illumina, but be aware that there's potentially 2. So as I said, we're going to extend out our SAM reader. So we're going to have 2 things here. We're going to have a file called quality string handler, and we're going to have a new version of SAM reader called SAM reader 2. So this will be the upgrade to SAM reader. So one of the things we're going to have to do, and this, by the way, is one of the important things when you're trying to teach yourself how to write a computer program, and not just teach yourself how to code, but actually approach writing a computer program. They're really kind of 2 separate skills, although they're obviously dependent on one another. Figure out what aspects of the program you don't know how to do. So I'm pretty sure that most, if not everyone here, didn't know how to convert characters into their ASCII values in Python and ASCII values into their characters in Python. The good news is a quick Google search actually tells you exactly how to do that. And the command in Python for converting a character to its ASCII value is ORD. So you do ORD and you pass it a character. And if you want to go from a character to its ASCII value, I'm sorry, if you want to go from an ASCII value to its character, you type in CHR and then you pass it the numerical ASCII value, at which point it returns the character. So char 33 is the exclamation point, just like we expected. So let's go and create a new class for quality strings, and I'll walk everyone through this before we start messing around with it. So again, we've defined our class, and we called it quality string. And since we know we're going to handle quality strings, it makes sense that we make this. And we kind of know what we want it to do, so we're going to write our initializer. We know that we want it to take in a raw quality string. And we also know, because I just showed it, that there's two different quality score encoding schemes. So we're going to have a base value, which will default to 33 because that's kind of the standard. And we're going to start off with an assert statement. And I just tend to like starting things sometimes with assert statements to make sure they're not getting anything unusual. So here I'm just assisting the type of quality string has to be a string. So if somebody tries to pass an integer here for some reason, it's going to throw an error. And then here I'm saying I'm setting that raw quality string to the attribute quality string, and I'm just stripping away any non-printed characters from the beginning and end. And then self.qualityArray, so that's another value, that's another attribute I'm setting, equals self.calculateQualityArray. So I know from this I'm going to need to write some function that'll calculate an array of quality scores. And it's going to need to know what the base value is. So here it says calculate quality array. So that's that function I just said I'm going to need. And I'm doing this pattern here. So anybody here remember from yesterday what I typically call this step? Just jump in and chat if you remember what I refer to this as. I did this thing and then I start a loop. So that's a pretty common pattern you see. Yes, I'm initializing an empty list. And you'll see this programming pattern with me a lot, and you'll see it a lot with a ton of other programmers where you initialize something like an empty list or an empty dictionary or an integer valued at 0, and then you keep adding to it or incrementing it or whatever. So in this case, it's iterating over characters in the quality string, and it's doing collection.append, so it's adding to the collection as it iterates through this loop. And it's doing the ASCII value of the character minus the base. So this is the formula for figuring out what the Fred quality score is from a given quality string character. So it's just the ASCII value of the character minus the base. And then after I'm done iterating through this, I'll have built up a nice collection of quality score values, and I'm just going to return it to whatever called. And of course, just like usual, I've overloaded string. So instead of printing out that weird thing that says quality string object at some memory value, it's instead going to print out the quality score string itself. All right, so going from our previous SAMline handler to our SAMline 2, we really just do a few small modifications. So we're going to import quality string handler, and that's going to give us access to that code that we just put in. We're also going to modify the self.quality line. So previously it was just storing the raw quality score sequence, but now we're telling it that it's actually a quality string handler, and so it's going to do all the fancier stuff on the quality array. And then a couple modifications down here. So we're going to actually print the line, and we're going to print the quality array. And that's just so that we can see if the quality array is doing what it, or the we're going to see if the quality string class is doing what it's supposed to here. So when you launch it, it's going to take a few minutes to read all the lines. But then what you see is that it prints out the line up here. And below that, it's printing out the raw quality score Fred scores. So I'll give everybody a minute or two to get that up and running, and then I will pick up again. I have a question from Sarah Chang asking if I can briefly explain what the double underscore means surrounding something. So in Python, a lot of people, when they refer to double underscores, they'll just call them dunders. So you'll typically see the double underscore surrounding methods that are being defined in a class, and typically they're sort of special methods for the class. So the init one is for initializing an instance of the class, and you'll pretty much always find init in things. The overloading actually refers to taking something that's built in for most classes, so it's already loaded with most classes, such as when I try and print an object that doesn't have specific instructions on how to print it, it'll just print as what type of object it is and where in the memory it's stored. Overloading something is the act of overriding the existing functionality. So instead of printing what kind of object it is and where in memory it is, for example, having it print out a list of quality scores, that's what overloading is taking an existing taking some functionality that that was loaded with the object, and then basically overloading it with something else. So the double underscores just kind of mean that something is a built-in method for the object, and you're giving it different instructions. So for Sarah, does that kind of help? Okay, cool. Let me know if you have any more questions. All right, so now we kind of have one of our first goals for this class. Oh. The last line of quality string handler should return self.quality string. Yes, it should actually return self.quality string. That is correct. I think it's correct in the code I gave you guys, but I think this one had a typo in it, and I keep forgetting to fix that slide. So yeah, it should be returned self.quality string. If you try and run it this way, what's going to happen when it tries to pull the quality string as a string value, for printing is it's going to probably give an error message saying that quality string is undefined because self.quality string is what's defined. All right, so we kind of have our first goal for the class. And actually, before we start on this, let's actually do a quick break for everyone, just because I like to make sure that everybody gets breaks at least once an hour. So we'll pick up back again at 2:20. And until then, this is a good opportunity for restroom break, stretching break, get some water. I'm definitely gonna go refill my water bottle. But obviously in this current time, it's a good idea to kind of, stay healthy and stay hydrated. So we'll pick back up at 2:20, and in the meantime, everybody's got a little break.
I'd like to say something before you guys go. Can you just write here in the chat room so I can take attendance? I mean, everybody. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. It's 41. There's 55 people in here. And maybe it's a bad idea.
All right, it's 2:20, so I think we can pick up again. I'll give everybody another minute or so just to get back to their computers if they were away. All right, so the goal of this next program is we're going to take what we've already done. So we're going to look through that SAM file, and we're going to look at the first 50 bases of every read with a length of 100 or more. And we're going to look at the distribution of quality in those first bases. So we're just going to take the first 50 bases and see what kind of a quality distribution we get. So this sounds like it's probably going to be kind of complicated, but let's try and break it down into a set of questions so we can figure out what do we already know how to do and what do we need to figure out how to do. So what do we already know? We already know we can break this data down really well. So we have our SAM reader, and we now have our SAM reader 2 objects. And we know that we can break down a SAM file pretty effectively. We know that we'll have to filter on read length, but that's pretty easy to do because we're already storing read length. So that's simply just doing a greater than operation. We know that we'll have to iterate over the read lines and build up a matrix. So in order to do a histogram, we'll have to build up some kind of an array or matrix counting how many times we see each value, because we need that for building up a histogram. We're also, we'll also need to take an average across each row or in the reads. And we know that we'll have to generate a histogram of these values. So what do we not know how to do? We don't know how to build a matrix, but a matrix is really a 2-dimensional list. And we know that we can start initializing some empty lists and just start adding stuff to it. So building up a matrix is probably not that painful. We know that we'll have to take an average across each row of the matrix. So everybody out there, put your hands up if you know how to calculate an average. I'm hoping I see every single hand going up out there. I can't imagine, I'd be very surprised to find out there's people in this class who don't know how to calculate an average. And yep, sure enough, I'm seeing everybody's hand go up. Okay, so calculating an average is not hard. You just need to know how many things you're looking at, and then you need to know what the total comes out to when you count them. All right, and then we'll have to generate a histogram of these values. And I suspect probably nobody out there knows how to generate a histogram yet. So we'll see if that's going to be difficult or not. So we're going to work on a new file now called histogrammaker.py. So usually I like to play around in the Python shell again just to kind of generate data structure, see if I can figure out how to do what I want to do. So in this case, I imported SAM reader, I read the SAM file, and you see here I'm just starting up an empty list called collection. I'm iterating over the SAM lines. I have my filter here to catch lines that are greater than or equal to 100 bases in length. And I'm just adding on the first 50 quality scores for each line if its length is over 100. And this line here is actually just saying that if the collection gets over 10 to break. And that's because I don't really need to build up the whole collection right now. I just need to see if I'm building up the data structure I want. So I tried this out, some very simple Python code. It's kind of the obvious way to build up this matrix is just iterate over SAM lines and keep adding the first 50 of each from each of these quality score value lists, just keep adding it onto the collection, and that's going to be how I build up my matrix. So my matrix should be of width 50 and of length however many lines I've read. All right, the next trick is turning a list of lists, which in Python is basically a matrix, into a NumPy matrix so we can process it a little bit more quickly. So first thing you gotta do is import NumPy. And in this case, you could, since NumPy is meant to work with Python, it's not too surprising that you can just create a matrix in NumPy by saying NumPy, create a matrix out of the collection. And sure enough, when I look at my data matrix, I have a matrix made out of the collection. So creating that matrix was not difficult. Then I said, okay, well, next thing we need to do is figure out how to calculate an average. And it turns out NumPy being a mathematically oriented Python package, you can pretty much just calculate a mean down each row by doing the matrix.mean and tell it which axis to calculate on. So you'll see this a lot in NumPy. When you're working on a matrix, you'll have to set the axis, and the axis will generally either be 0 or 1, depending if you're going down the columns or across the rows. So in this case, since I want to calculate across the rows, the axis is equal to 1, and that again says calculate across rows. And sure enough, I get back 10 mean values for the quality scores for the first 50 bases. Sorry for 1 second. I'm just going to respond in chat to a question I got. All right, thank you. All right, so going back to this. So we have now a one-dimensional matrix that's a bunch of rows, each with a mean for a different row in it. And in this case, since I kind of want it to be really more of an array, which is going to be a one-dimensional matrix that is just a row, that's very easy to do as well. I just do data means.transpose. And so now I have the mean of the first 50 quality scores for 10 of the values from the SAM file. So now I just have to put that to work in the program. So this is, yeah, so here I'm just setting some values, read length minimum and analysis length. If you're trying to put a program like this into production, you'd probably be taking these as arguments, but we don't have to worry about that for this. So here we're doing get quality mean matrix, and we're just defining a function for it. We know we need to take in the SAM file. We know we need to take in our read length minimum. We know we need to do our analysis length. So read length minimum is sort of our filtering value. We get rid of any reads that are shorter than that. Analysis length is how long we're reading in there. Analysis start position, that's basically the position we start looking. So for example, if we want to ignore the first 10 bases, we would say analysis start position equals 10. And then data limit equals false. So data limit we can actually use to limit how far we go in when we generate this matrix. As usual, I start with an assert statement. In this case, I'm saying the read length minimum has to be greater than or equal to the analysis length plus the analysis start position. So essentially what I'm checking here is I'm making sure that I can't be reading past the end of a read. I'm importing my SAM reader 2 in my NumPy, just like before. And I'm using the code that I just demoed in the Python shell, just showing that here I'm reading SAM lines. I'm initializing the quality list. I'm adding to it iteratively, converting it to a matrix, taking my mean, taking that and calculating the means on axis 1, which basically means going across the rows and calculating the mean. and then returning the mean matrix, which I can either return transposed or not, depending on how I wanted it. In this case, I don't actually care about getting it transposed, so I'm just returning the mean matrix. And as far as making a histogram, it sounds really complicated, but there's something called matplotlib in Python that actually takes care of plotting data for you. And it turns out creating a histogram in Python is actually trivial. So this is the entire function right here that it takes to create a histogram. So we're defining our function. We're going to pass it a mean matrix. We're going to import matplotlib.pyplot. And this one I tend to import as PLT. So you can actually change something's name when you import it, which is really useful. And the nice thing about importing it as PLT, this type's a lot easier than matplotlib.pyplot, which, even though this name is actually long, it's just the way the letters are structured makes it even more awkward to type. And I'll answer the question in chat really quickly. Did somebody unmute themselves accidentally? All right, and I have a question asking, does it matter where in our code we import libraries, inside the function or outside? It matters for certain things. I've actually tended lately to be importing outside my libraries more. It depends on personal preference. I used to import a lot more inside my libraries because it made them, it made it so I could copy and paste it more. But then as I started getting more into writing my code with the intention of making it reusable from the get-go, and for building out reusable packages frequently, I started doing the import outside. And if you start doing something in Python called type hinting, which is actually a good practice to get into, although I don't cover it in this class, then you absolutely need to start doing your imports outside of your functions, because you'll sometimes need those classes when you're defining your functions to type hint. And type hinting would just be saying, for example, that this mean matrix is expected to come in as a Numpy matrix. So for Mo, does that answer your question? Okay, cool. So anyway, with matplotlib.pyplot, this one tends to be a very confusing object for people, because a lot of people see objects as doing something with your data and returning something. So matplotlib, don't see it as something that returns your data. Matplotlib.pyplot, it's a lot easier to understand if you think of this as your canvas. So it's actually there and you're just drawing on it, and at some point you can choose to look at it. And it turns out that to do this, this has a lot of drawing functions, or a lot of plotting functions built into it. So if I just call plot.hist, that actually tells it draw a histogram on yourself. And I pass it the data saying just mean matrix, and I tell it specifically I want 41 bins so that it doesn't try and automatically figure out how many bins to do. So kind of cool. This one line is, or I should say these two lines, import matplotlib.pyplot as PLT, and then plot.hist, and give it the relevant information. That was all it took to draw a histogram. The only other things I had to do for making the histogram then are give my plot a title, label my x-axis, which is done by xlabel, label my y-axis, which is done by ylabel, and then I can either do plot.show, which will generally make the plot pop up in a little pop-up window on my screen, or I can tell it plot.savefig, which will tell it to save it to the nearest folder. So right now it's set up so it'll save the figure. If I uncomment the show line and I comment out the savefig line, then it'll just pop up the plot in a new window. So going on, we have our test code down here that's going to actually run things. So quality mean matrix, and this will tell it to get the quality mean matrix that we need. It'll print the matrix shape just so that we can see how our matrix is shaped. And then make histogram. And that'll actually tell, and giving it the quality mean matrix will give it everything it needs to make the histogram we need. So I'm going to give everybody a few minutes to mess around with this. Try playing around with it. Feel free to mess with the bins. See how you can make the histogram a little bit different. But you should get something that looks like this in the end. All right, so it's 2:35 right now. This one I usually like to give people about 15 minutes to play around with. So at 2:50, we'll pick it up again. Definitely raise up a hand if you have a question, or if you see something really cool, feel free to let us know. But learning matplotlib is usually one of the key points for Python for a lot of people, and it does take some effort, but it winds up being really rewarding because you can, this is basically how you can start automating figure generation, and you can generate plots here that you can't do in Excel. Oh, I have a question in chat. Oh, wait, no, I don't have a question in chat. That's an old question. Sorry, I didn't realize I muted myself there. If something is taking a while running, you can hit Control C. But if it takes a while to load the, if it takes a while for the first step to load the SAM file, that's perfectly normal. So what you should typically observe is that when you first start off, it's not going to do anything for a couple seconds. And then it's going to say loaded about 500,000 lines. And then you're going to see stuff happening really quickly. All right, so to answer the other question, there is something, so there isn't really a busy like you see in MATLAB, because Python is its own programming language, so it's not like MATLAB where you're just programming in an environment. And the real program is actually MATLAB. So in the case of Python, you can definitely build in counters to your programs, and I do sometimes build in counters for things, but the counter or the statement of busy only exists if the programmer puts it in there. Right. What's the best way to set working directory in Python at the start of a script? It depends on what you want to try and do. You can always access things through absolute path, or do you mean set a working directory for accessing Python packages? Okay, so for that kind of functionality, typically what I'll do is I'll just have a program where people can set a working directory, and then I build up the paths around the working directory. And if they don't set one, then I just take the current working directory. But there's a few different ways to do that if you ultimately want to do that. All right, and then I have a question. What is the best way, if we want to save the quality by read.png in a specific folder, how do we do so? So if that's what you were trying to do, I'll go up a little bit. So the thing that saves the file is this command here, plot.savefig, and then it's saving it to quality by read.png. So because I didn't specify a folder, it's just going to save it to the current working directory. If I gave it a full path here, it would save it to that folder. So does that answer your question? Okay, looks like I got it. All right, and actually, since somebody's already saying they have to go to a group meeting, we've actually hit the end of the day 2 material. So usually in class, this takes a lot longer, I think in part because I usually wind up running around from computer to computer a lot. So yeah, we're done actually. So today we're done pretty early. I'm gonna stick around and answer any questions for a little while. And once I'm done with, and then once we're done here, everyone's free to go. But as I said, I'll hang around and answer any questions for a little while. So I have a question. Can I explain how, I have 2 questions actually. So the sample data.sam file, it should be in the same folder as you're currently running from. So just make sure that Spider has the right current working directory. And From Ja Wang, I have a question. Can I explain how the bins work? So if you're familiar with the idea of histogram, histogram is just going to have a certain number of bins. So the histogram should generally look about the same no matter how many bins you pick. If you start picking too high a number, you may get some unusual things happening. But what will happen is if you pick a low number, like you go from 41 bins down to 10, you're going to notice that it becomes a lot more, you'll smooth it out a lot and you'll see a lot less detail. So that's really all the bins are for a histogram. All right, so on a Mac, the easiest way to get the path of a file is, it's been a little while since I was working primarily on Mac, but I believe you're going to do a right click or a control click on the file name or the directory name. And then I think there's an option to do something like view information or something along those lines. And in there, you should see the path to the file. And you should be able to actually highlight that and then hit Command C, and you should be able to copy from that. All right, so I have a question if I can explain the role that the parameter self plays. So self is kind of an interesting one. It takes a lot of getting used to, but for most methods in an object or for most methods in a class, you're going to pass it a self, and that's basically saying it's this current instance of the object. And there's very few times where you won't. So a lot of times you can almost treat it like part of the scenery, like you can just assume it's there. There's very few times where you won't actually have it there. And really the times where you're not going to have it there, that starts getting into kind of more advanced technique. And I don't really cover that in this class. So you can pretty much almost treat it like part of the scenery. All right, couldn't get the file path working on a Mac and terminal. Ah, you tried typing the path. Are there spaces in the path? Okay, there's no spaces. Oh, you actually typed the word path? Okay, so path does something else. You would actually, so when I say path, the path to something is, yes. So actually in Python, you'll need two commands to do it. So the first command you'll need is import OS. Oops, oh, sorry. First you'll need import OS, and then os.getCWD will give you the current working directory. All right, so it's saying no module name samreader2. I think I know the reason for that. Give me 1 second to double check something. Yes, where it says samreader2, check your capitalization. I think the first R in reader should be capital. Okay, so if it's not finding samreader2 that way, there's a good chance you're in the wrong working directory. All right, so for the question of somebody who said they saved all the files to the same directory and is not finding them, put in the command to check your current working directory and make sure that when you run, and just insert that command somewhere early in your program and have it print out the current working directory and make sure that the current working directory the program is in is the current working directory that you think it's in. Sure, so I'll give you the command to insert. You want to put this somewhere very early in your program. If you run those 2 lines, just insert them somewhere very early in your program before it tries to load anything it can't load. It'll tell you where it thinks it is. All right, so I think if there's no more questions coming in, I'm probably going to disconnect. If anybody has any questions, I'll wait a couple more minutes so you can get them in. Otherwise, I will see everyone tomorrow.